Yeah. I saw you had updated or you got the interface working. That was really cool.
The interface is really speedy now. It's really, really nice.
Yeah.
And I am closing in on getting the remote sensing page working again, um, with the same
Oh, nice.
speedy interface. So I am almost done with this round of the software,
Oh,
which
wow.
is a huge, heavy lift. So pretty
Yeah.
excited about it. Very excited about it.
So how'd you get it to be faster then?
So um, I found out that, okay, well, so first of all, a future software lesson. Um, Scope is really important. Um, so if you, no, we'll talk about that later. But scope is really
Okay.
important. When we get to talking about scope, it's going to be really important. All right.
Okay.
How did I make it faster?
Yeah.
So what I did was I made a little routine to check the inputs and made it so if there isn't any input, it just goes back to where it came from.
Mhm.
Um, and then I found out through the process of digging into the library, um, for one of the sensors, um, that um, so like the big sensor that we use, the 18 channel spectrometer sensor, um, if you read all 18 channels, it's going to take a while. And
Yeah.
most of that time is spent just pushing bits down the I squared C bus. Um,
Yeah, that makes sense.
so it's just not very fast. Um,
Mhm.
so it turns out that in the library, um, the way that you ask for the reading of a particular channel is unique to each channel. So that means that you can then ask one channel to give you its report and then go check inputs,
Mhm.
right? So instead of doing all 18 channels and waiting for all the data to come through,
Yeah.
you go, oh, let me have that channel. All right, check the inputs. Okay, let me have that channel. Check the inputs. Um, and so the amount of time that you spend not being able to check the inputs is kind of on the order of a tenth of a second or something like that. So that's the amount of time it takes to blink. Um,
Yeah.
so from an interface point of view, that's acceptable.
Okay.
And it's way better than waiting for almost 2 seconds for the thing to respond to the twist that you gave to the encoder.
Yeah.
I was saying, like, if you get an input, set a flag, and then crash through the rest of the program to handling the input.
Yeah.
Right. So that meant in a whole bunch of places I had to say, if you see an input, don't do these things. Okay.
Yeah.
So there was a lot of that kind of questioning. So now what I've done is I put that in the input check routine. Um,
Mhm.
so I don't care if you've seen an input or not. Go to the routine, and if you haven't seen an input, come back,
Yeah.
right?
Yeah,
So
I
then
guess
you're
maybe
doing
that
it
is
only in one
easier.
place. Um,
Yeah. That's cool.
so then I don't have to ask that question a gazillion times. I just say, go check the inputs.
Yeah.
And between that and the doing it one sensor at um, one channel at a time, um, and the way I did that was pretty clever too, which is I just turned each channel into a sensor. So then I can say for any of the sensors that are there, read them. So I don't have to do like if it's a spectral sensor, do this special case thing, right? And read all 18 channels in whatever order and yada yada yada. It's like,
Yeah.
nope. And that part of that was that new structure for the data file. Um, is that it just doesn't matter what sensor you're looking at. If it's a spectral photometry sensor, that's one sensor. And you
Yeah.
put down the information and you write down that sensor and then that's that. And then you go on to the next one. Um, so
Wow.
yeah. So then
Yeah.
on the all sensors display page, you can show each channel one by one. So if you're interested in blue, because it's in tight.
Excuse me. Thank you.
If you're interested in blue, you go look at the blue channel.
Yeah.
And you see the values right there, right in front of you. It gives you a small enough set of information that you can actually make something out of it in your mind. Um,
Yeah.
so whereas if you have a table with 18 channels on it and you're doing all of these things and it's like you're trying to process all the numbers all at once, just
Yeah.
go look at one channel. Um,
Yeah.
yeah.
Yeah. I'm definitely going to probably stop taking photos of it now and wait until I do my second build
Uh-huh.
because I mean, like you said, the wires are just so. Once you
That's
build the first one, you have a better idea. But even when I told you I like messed up I accidentally like grounded and or bridged ground and power together, and I had to fix it.
right.
I had to like I ended up soldering it or like putting the wire on the back side of it instead of the front side because
Uh-huh.
there was just no way I was going to be able to get it back through where I need it to. So I have like this one really long red wire that like loops all the way around the back. It's
Yeah.
almost like it's like a phone case holder, but it's fine. It'll fold in and I'll make it work.
Yeah, the running wires on both sides of the board is what I did with the Stella 1.1.
Mhm.
Um, and then you have to explain to the person who's doing the assembly that this goes on the
Which
front and this
some,
goes on the
yeah,
back and which goes where and all of this kind of stuff. It is much cleaner to do all the wires on the front, but that doesn't mean you have to do all the wires on the front.
yeah,
Um,
yeah.
so yeah, um, if you end up with a working unit out of this first build, you are doing really, really well. The
I'm not,
chances of you working on developing a working unit on the first build is pretty low. Um,
yeah.
on the
I
other hand, you're PFC obsessive, so we'll take
what
a
did
look
that
at
stand for? Principal Chief? What was
that.
it?
Private first class.
Private first. Yeah, that's what it was. Gotta write that down. I could not remember it, and I was trying to tell Matt the story. But yeah, I don't have the highest hopes. Um, I've like medium. Well, we'll say I have reasonable expectations and high hopes.
Okay.
So I'm
Yeah,
hopeful that it works, but I've already like told myself I wouldn't count
well,
on
you're
it.
doing everything you can to try to get it to work. And
Yeah,
if it
yeah.
works, great. And in the high likelihood that it doesn't work, you'll get to kind of
Well,
figure out how to figure out what's wrong with it. So,
yeah, exactly. The only th I mean, obviously I won't know if it works until everything's done. All the test codes are working perfectly except for the display, which I don't know. I'll have to like double triple check.
so you said, how do you bridge the jumpers on the back of the screen,
Right.
right?
For the
And
yeah, for the display.
yeah, and you put a blob of solder on them to connect them together. However,
Mhm.
they don't want to connect together. There's a natural surface tension issue there. Um, so if you put a blob of solder on there and you just let it kind of sit, it'll be two blobs of solder, one on one side of the jumper and one on the other side of the jumper, and then they're not
Yeah,
connected. So this is for jumpers, what is it, IM 1, 2, and 3, but not jumper IM 0. Um, And so what you have to do is you have to either figure out a way to break the surface tension enough, put enough solder on it. It feels like much too much solder. Um,
Yeah,
Put enough solder on it that it becomes one big blob. Or you can put a little piece of wire across the two pads and then just trim off the excess.
gotcha. So I think I just filled them in. I didn't bridge them together.
Yep. Well, because
So
it's the
that's
first time you
definitely,
had a solder bridge to do. Well,
yeah. The
intentionally
first,
anyway.
yeah, the first intentional one. Yeah, probably skipped ahead in Mike's video. I was like, oh yeah, he filled it in.
Yeah.
Perfect. Yeah, so that will definitely, well, hopefully be the fix I need.
It is certainly something that would stop it from working. Um,
Yeah.
the purpose of closing those jumpers um, is they tell the screen to expect one bit of information at a time.
Mhm.
There's another mode where you can run 8 wires over and send one 8-bit byte at a time. Um, right? So it's the equivalent of having um, you know, 8 uh little video channels open on your screen all playing at the same time.
Yeah.
If you were able to process that information, you'd be getting the information 8 times as fast,
Yeah.
right? And so the screen goes, oh, okay, I'm going to stick my, you can also do it with your fingers, not your thumbs, right? So you have 8 fingers. And then if you get a wiggle on one of them, or on 6 of them or whatever, you get that information all at once. Um, but that requires 8 wires. And the microcontroller that we're using, the board that it's on, only lets us have a certain number of pins, and we've used them for everything else. Um, so we could make the screen display much faster if we had more pins, but then we would need to do something else with the pins. Um, we would need to come up with more pins to turn on the 5-volt supply and um, let's see, what else are we using those pins for? Um, do the,
So,
data command exchange on the display and do the
mhm.
um, what else are we using the pins for? Um, I don't remember. I'd have to look at the schematic. But we
Yeah.
use all the pins.
Yeah.
And we want to have a pin or two. Oh, for the analog input that comes from the magnetic coupler, we need a pin for that. And so anyway, we've used up all the pins. Um,
Yeah.
so
I know we talked about the pins are where they are because they fit nicely there. Otherwise, it would
okay, so
be,
which pins are we talking about in this particular case?
I'm thinking like the 3 and the 4 pin, like maybe I'm not in the right pins.
Oh, the magnetic coupler.
Yeah.
Yeah, yeah.
Oh, those
Okay,
are
those
pins.
pins.
Those pins, yeah. Or wait, were those not the pins we were just talking about?
No, no, no. On the microcontroller, which you've already put onto the board,
The microcontroller pins. Okay, yeah, yeah, yeah.
there's
Okay, that
a
makes more
bunch of
sense
holes
then.
there all the way
Yeah,
around the
okay.
edge, but there's still only, so many of them. And
Right. Okay.
taking up 8 out of the whatever, there's like 12 of them available or something like that. And using
Yeah.
up 8 of those means that we only have 4 to do all the other things that we need to do. Um,
Yeah.
so
Okay, that makes more sense. Like, so it's like we could just add another pin.
yeah.
We can just add another pin. That makes sense. Um, how does I know we talked about like I'll learn this later down the line, but
Okay.
actually like designing board and where everything goes, how much of that is just like Tetrising it, kind of seeing where things fit and then having to like remove and try again versus how much is there like kind of a pattern to it? Like going in.
Um, Experience helps for sure.
Yeah.
Um, but one of the ways you get experience is by building a bunch of them. I've
Yeah.
probably gone through 10 prototypes where I got most of the way wired and realized that I'd boxed myself into a corner. Um, so, um, so you start with a schematic, an electrical schematic, and we'll talk about how to read those probably not today. Um,
Yeah,
but what it says is from the electron's point of view, who's connected to who?
yeah,
Um, right? So this pin has to connect to there, and you draw the wires on the schematic saying, all right, well, this is where the wires go. Um, and I did a fairly strange interpretation of a schematic for specifically the 1.2, trying to make the wires more or less where they are on the physical board.
hmm,
That's not typically what you do with a schematic because it takes a whole lot of work. Um,
yeah,
but I wanted it to match reality pretty well, like physical layout pretty well.
yeah,
So that for somebody who's only seeing a schematic for the first time, there aren't a whole bunch of wires that just sort of vanish and show up someplace else. Um,
yeah,
so but so you start with a schematic. You say, all right, I want the electrons on this pin to connect to this pin. Um, and then you say, all right, I'm going to do that on this board that I have, on the prototyping board that I have, um, that has this many positions that I can solder to, right? So you think about those boards and they have, what, 5 positions on either side of the center. And those are all connected. And then so you say, okay, so those are already connected. That's nice. If we can leave it that way, that's even better.
yeah,
So we don't have to cut the traces all over the place. Um,
yeah,
and you right. So then the other considerations are things like, okay, well, I need the magnetic couplers to be at one end. Um, I can't have them off the side because they don't really work there, and I don't like the physical layout of that. So then on the
yeah,
other end, I need access to the USB connector. So that
mhm,
kind of tells us where the microcontroller has to go.
right,
And then the microcontroller could go centered. No, it can't go centered over the center of the prototyping board because it has an odd number spacing.
hmm,
Um, so you have to put it either one to the left or one to the right, or one toward J or one toward A. Um,
hmm,
and then you have to figure out, okay, well, if I put it in this one, do I have access to the things that I need to have access to? Um, like you could put it in row A and connect it to row, uh, let's see, F, right? Connect the other side to row F. But then all of the B, C, D, and E holes are covered. And
yeah,
that's going to be really irritating to try to put the wires in. And then you have to run wires on the back. And then you have to make sure that when you're poking them through to solder them, that they don't touch the board that's on the other side. Um, right?
yeah,
So can be done, not very elegant.
yeah. That makes sense.
And then things like, the display breakout, you need to have access to both sides of it.
Yeah,
Um,
yeah,
the clock breakout board, you want to have access to the battery, so you can put it on upside down so you can actually get to the battery.
yeah,
Um, Also, because if you put it battery side down, the battery connector, the battery holder will short to whatever's underneath it. It is literally tens of thousands of decisions like that.
yeah. So is it typical to like 3D print parts to help that, like the battery holder, battery spacer and stuff?
I typical. I don't know what typical means in this context.
Yeah, I don't know.
Um, so people use plastic parts all over the place, and if you don't 3D print them, which you couldn't do up until 10 years ago,
Yeah,
um,
that's
right?
true.
You would have to get those plastic parts made usually by injection molding. So you'd have to decide on the part ahead of time and make a mold for it and squirt some plastic
Yeah.
into it and let it cool, and then get it out of the mold and use that, right? So almost all electronics packaging is made that way.
Hmm.
So if you think about a, kitchen timer or something like that, right? Um, Nowadays they're made with an two injection molded parts screwed together. So spacers, like for the clock module, um, are super nice to have, and we can make them
Yeah.
because that's the requirement for this
Mhm.
board is that you need to be able to make 3D printed parts, or not for the board, for the
Yeah.
unit. You can build the whole thing without any 3D printed parts. Um, it gets a little awkward to put it together. It'll still work.
Yeah.
Um,
Just makes things better.
yeah, and then the
Yeah.
like the did you actually print the main assembly fixture? Good. Yeah. So fixturing is something that people who are new to engineering don't think about. And it takes you a while to get to it. And it's like, oh, I could make this a whole lot easier if I had something to hold that still for me instead of
Yeah.
trying to, wave around in the air and put these things together. Um,
Yeah.
it's like, when we have all these examples of ancient architecture that have arches in them, right? And you think about it, it's like, well, how do they build an arch? Because it's a self-supporting structure. They built scaffolding and they held it up with scaffolding.
Yeah.
Um, and then once they had the arch in a position where it was self-supporting, they could take the scaffolding away. We don't have
Yeah.
the scaffolding anymore because they took it away.
Yeah.
Right? So all you see is the arch, and you're like, well,
How'd they do that?
yeah, how do they do that?
Yeah.
Um,
So yeah, very similar to the assembly fixture then. How'd you get everything to stay in place?
right.
You don't see that anymore if you're just using the Stella.
Yeah, and getting the magnetic couplers to be in the right position is really important. Because
Yeah.
otherwise they won't connect to the other things that you're trying to connect them to. Um,
Yeah.
and in fact, Mike has been pestering me for because you can bend them out of position a little bit even after you've installed them. Um, and so Mike has been asking me for a post alignment fixture, so
Hmm.
that you can check it against something and adjust it if needed.
Yeah.
And from my point of view, I think it would be better, although there's not a lot of room, to have a permanent plastic part in there that would hold the magnetic couplers in the right location, like the spacer for the clock does.
Yeah. So it'd probably be you have to go like on top instead of on the side, like the curved one, right?
Yeah,
Otherwise, what's the point of the magnet?
right. And there, you can't really have it if you're going to have a permanent part like that, it has to be not in the way of um, running the wires. It has to be not in the
Yeah.
way of cutting the traces if you've forgotten to do that. Um,
Yeah.
right? If you have a plastic
Guilty.
part covering it and you solder the whole
Yeah.
thing down, then you're in a spot. Um,
Yeah.
so, but I mean that's the process. It's like, oh, all right, I'm going to run this wire here from here to here because that's where it needs to go. And I can fit these components on there. I could get more pins if I used um, an I squared C bus pin multiplier. Um, you can't use those for the display because the display has to use fast pins. Um,
Yeah.
but then you're only using the I squared C pins. I don't have any room to put that on there. So right now, that doesn't seem like a good idea. Um, well, especially now that I've got the thing running at a reasonable speed, um,
Hmm.
which was not a problem of the display update speed. Um, so I just discovered that in addition to taking up less space, unsurprisingly, now that I think about it, modules that you've converted to this MPY format instead of the PY format, which we'll talk about in a second,
Hmm.
um, run a whole lot faster. Um, so what's the difference? So PY is Python, right? So that is a human readable pseudo-English Python language code, right? So you can look at
Yeah.
it, you can go, oh, okay, I can read that. Um,
Yeah.
and the Circuit Python interpreter looks at it and it goes, oh, well, Bianca wrote this here, and that means that I have to do these things in the computer, right? In the
Hmm.
actual processing. These digital
Yeah.
things need to happen. Um,
Hmm.
if you convert a .py file to a .mpy file, M for uh, micro Python. Um, and what you do is you do the steps that the interpreter would need to do, but you do them ahead of time.
Mm.
And so you give it a set of instructions that are totally unreadable to a human
Yeah.
that tell the computer bit by bit what to do. So that means that the interpreter doesn't have to interpret. It just goes and says, oh, I do this. Okay. Instead of, oh, Bianca said this, then I need to figure out how to do this. Um,
Yeah.
so because it's not human readable, you don't have all that human readable garbage in there. It's a lot smaller.
Yeah.
But that also means that you can't edit it on the fly because it's already compiled for you. It's already in computer read only form. So, and you do that with a precompiler called MPY cross.
Hmm.
And so you just take your little file and you say, all right, MPY cross act on this .py file. And it spits out of that .mpy file already compiled.
Gotcha.
And that you have to do from the command line, um, which is something you'll have to learn eventually. But you cannot take an MPY file and turn it back into a .py file because the whole point of converting it into an MPY file is to lose all the information that you don't need to actually operate it. But you need all of that information to turn it into something human readable.
Yeah.
So you need what's known as the source code, right? The source code is the stuff that you can read, the source that the operating code comes from. And the operating code or the compiled code um, is for the computer only. So that's a one-way process.
That's interesting. It can't go back and forth. Like it can only go in the one direction.
Well, that's what happens when you lose information.
Yeah.
Um,
Yeah.
okay, so here's the thing. When you experience something, you make a memory. That
Hmm.
memory is a change in the complexity of your brain, right?
Hmm.
Specifically, your brain gets more complex because you've
Yeah.
now added new connections in your brain,
Hmm.
right? That's why you cannot remember the future. So even if, which we suspect, all time was created at the Big Bang, we only move through it in one direction because of entropy and information,
Yeah.
right? Um, so things like colliding billiard balls can work in, forward or backward in time. Um,
Yeah.
but things like, and this is one of the appeals of burning things, if you burn like a piece of paper, paper doesn't unburn. It doesn't
Yeah.
get less entropic, right? You're taking all those paper molecules and you're scattering them into the air mostly. Um,
Yeah.
right? Um, it's really, really hard to take a bunch of paper molecules from the air and put them back together into anything, much less the paper with the writing on it that you started with. Um,
Yeah. Hmm.
yeah, it's kind of like unstirring the sugar out of your lemonade.
Yeah. You can't really do it.
You can't do it. I mean, it
Yeah.
is
It not to the original extent.
well, and you can do things like you can filter off or cancel out the acid of the lemon, um,
Mhm.
and then evaporate all the water and you'll get sugar back.
Yeah.
Right? So there are ways to do that. All of those things take energy. right? So anyway, entropy only moves in one direction.
Gotcha.
So if you take something that has more information in it and turn it into something that has less information in it, there's no way
You
to
can't go
read.
back. Yeah, no way to go back to get more information.
Right.
We'll get that same information.
Because you've burned that information. It's no longer there.
It's
This
scary.
is why you want to hold on to your source code. And
Hold
you
on to your
can, with
source code.
sophisticated tools, take a compiled file and kind of try to reverse engineer it from the computery stuff to something that you can kind of read. Um, that works. You won't get what was there before. Um, oh, let's think about it this way. If I send you a design file in SolidWorks,
Hmm.
okay? If I send you the exported file, like in a .step format or something like that, you have all the
Hmm.
geometry, but you don't have how I got there. You don't have the history of it,
Oh, yeah, yeah, yeah. That makes a lot of sense then.
right? And that means that you can open it with something else that can deal with the geometry, but not the history,
Right.
because you strip the history off. Um,
Yeah,
but if you're interested in learning about how I made that part, without the
I
history,
want
that's a
that.
bit
Yeah,
irritating.
yeah.
Then you're making inferences and guesses. Um,
It's actually a really good way of putting it. Thank
yeah.
you.
Um, so one of the things that we want to do is we want to get you to the point that you can write programs on your own. Um, and the thing to remember is that you're never writing programs on your own because you're using tools that other people developed, including the language, um, including the libraries, including the concepts behind programming, right? All of those things. Remember,
Yeah,
we talked about human beings banging rocks together,
yeah, and telling
and telling each
stories.
other about it, right?
Yeah,
If you do not have the stories from all the other people who banged rocks together, it's going to take you a really long time to do anything.
yeah,
And you just can't. You
yeah.
don't have the resources to do it, right?
They
So
burn
you
the source code.
yeah, right. So I mean, so you could go to the beach and grab some sand, but then you'd have to figure out how to get the silicon out of the sand
Hmm.
and purify the silicon and then turn that into a chip. And then you'd have to figure out how to make transistors on that chip. And you'd have to invent all the tools needed to do that. Um, right? So like going back to the beginning is just it's virtually impossible and not particularly useful. Um,
Yeah,
I was thinking about this the other day. We only had cars for about 100 years. Right? Never mind airplanes.
yeah.
So we get so used to them. But you know, if I wanted to go to New York pre-car, it would take me 2 weeks to get there.
Yeah,
Right? At sort of best pace, it would take me 2 weeks to get there. Um,
yeah.
so
Let alone not getting lost. I guess we'd have a map, but
yeah, but you know, if you don't have a satellite or an airplane, the maps are going to be, you know,
outdated
well,
usually, or
they're
not
going to be only as
geolocated.
good as the people running all over the hills taking their chains with them. Um,
Yeah,
right? So this is one of the units of distance is a surveyor's chain, um, which is so you would literally take a chain with you because chain doesn't stretch very much, right? You wouldn't want to use a
yeah.
surveyor's rope because it would change length on you, right? So you put a spike in the ground and then you walk whatever it is, 30 meters, till you get to the end of the chain, and then you just put another spike in the ground. And that's how you make a map.
That's crazy.
And the only way that you get two-dimensional information out of that and not one-dimensional information out of that is by taking the chain and turning it to right angles and running over there and putting a spike in, um, and you know writing down where it was, right? No GPS.
Yeah.
Yeah.
Anyway, Stella.
All right, yeah.
No,
So what
no,
else?
no,
What else is going on?
yeah, yeah. I hope I can get it built this week. Obviously, that's we'll see.
Yeah,
I'm so close in terms of like what I've done and how
yeah,
many wires are on the board.
yeah.
But that doesn't mean anything if they're if even
Right.
one of them is a little bit wrong.
Yeah, yeah, yeah. Right. It's what we
So
talked about before is there's a million, actually probably an uncountable number of ways to make it so that it doesn't work. Um,
yeah,
and very few ways to make it so it does. Um,
yeah,
so yeah. So like if there's room and you put the wire in B instead of A in the same column, like it'll work. So there's at least two ways to do that. Um,
yeah,
but that's about it.
yeah. Much harder than building
Have
the
you figured
cube.
out the color scheme? Or have no, I guess it's all clear from the chart there, from the build list. Um,
Oh, well, what the wires are? Yeah.
right, yeah.
Yeah, so black is ground, red is power, white or green. One of them is SCL, one of them is IC squared, or I squared C.
They're both I2C,
Oh,
but
okay.
one of them is clock and one of them is data.
Oh, that makes sense
Did we
then.
talk about clock and data yet?
I don't think so.
Okay, so suppose I am sending you a message
Okay.
and I'm trying to do it by drum. Okay, so all I can
Okay.
do is hit the drum,
Okay.
right? If you're willing to wait a long time, I can do like 3 hits and then wait a whole bunch of time, and then like 2 hits and then wait a whole bunch of time, right? And then you'll know that that was 3 and 2 that I was sending, right? But suppose I want to send something at a higher rate. So if I send one drum that's keeping the beat, right? So that you know how much time has gone by, right? And you go tick, 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 and then you hit the other one sometimes, right? And so then you can go 1, 2, 3, space 1, 2, 3,
Hmm.
because you know how long the space is, and so now the space becomes meaningful. That
Yeah.
space is 3 drum beats long, right? So you can send information that way. And so that's why we use two-wire communication.
Right.
And that is true of USB as well. The protocol is different, and USB is much faster. Um, but the and protocol is just how many beats means what piece of information. Um, how do you translate from beats on and off to meaning?
Yeah.
That's what
Sorry, would you
protocol.
call it two signal communication?
Two wire.
Two wire. Sorry.
So typically you've got 4 wires running around. You have power, ground, and data and clock.
Hmm.
And it's not that the clock and the data are fundamentally different. They're still pulling the wire to high voltage or low voltage. High in this case is 3 volts, and low
Yeah.
is 0. But the clock is doing it at a regular pace.
Yeah, that makes sense.
And what's interesting about I squared C is that anybody can become the ruler of the wires. But what it means for I squared C is that anybody can take over the wires. They can be the main. And the way they do that is they wiggle the wires to see if anybody else is using them. So they use a transistor, which we talked about,
Yeah.
and they use a transistor to try to um, pull down on the wire to see if they can lower the voltage level to near 0.
Hmm.
And if somebody else is using the wire, then it'll sometimes be high because they're putting power into it. Um, and they go, oh, not my turn. I gotta wait my turn. Let's keep an eye on that and see if the wire is still wiggling. And the wire stops wiggling for a little while. We'll wait, and then we'll wait a little bit more, and then we'll say,
Try
okay,
again.
can I use the bus now? Wiggle, 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 wiggle,
Mhm.
wiggle. Hey, the bus is clear. I can send my clock pulse out that wire. And so everybody else is now following my beat. And I can send my information. But typically, what happens in all communication systems is that you send a command to one of the other devices saying, query is typically the
Mhm.
word, right? So if I ask you what you had for lunch, that's a query,
Yeah,
right? So what did you have for lunch?
need
You
lunch.
didn't eat lunch. Nothing.
No,
None.
no, no, no. I take back. I take back. I had like brunch. I had like those sausage biscuits.
Okay, so you had sausage
Yeah,
biscuits. All right.
yeah.
So
What did you have for lunch? It's
none
another
is a
query.
perfectly acceptable answer, by the way.
Yeah.
Um,
Okay.
so in terms of communication protocol,
Yeah.
so I had chicken dumplings, Chinese chicken dumplings for lunch.
Oh, yum.
Yeah, they're really good.
Yeah.
Um, I started that query chain, right?
Mhm.
So I said, "What did you have for lunch?" And you then told me what you had for lunch, and then you asked me a question, right? So I'm still in control of that part of the conversation, right? And that's typically what goes on in communication systems is one element of that communication system is in control and controls the timing and
Gotcha.
supplies the clock. But in the case of I squared C, you can anybody can control the clock. But
Sure.
the only way they can do that is by checking to see if it's all clear. So if you and Matt try to both talk to me at the same time, it's going to be really hard for me to understand either of you.
Yeah.
So we just have to make sure that there's only one person talking at a time.
Makes sense.
So um, the other communication system that we use, well, there's several. We use USB, right, to talk to the microcontroller between the computer.
Hmm.
But we also use SPI, which is known as Serial Peripheral Interface. And in Serial Peripheral Interface, there's only one main part. And what that main part does is there are a bunch of extra wires. And they're known as chip select lines. You've probably seen them. Um, like SDCS is one of the ones that you have to run on that thing, which we
Oh,
have
yeah,
gotten
yeah.
to, right? That is the SD card, secure digital card, chip select line.
Oh, okay.
Okay. And then there's a like TFT, I think we're calling it, which is the screen CS. Um,
Hmm.
so if that chip select line is pulled, I forget which way it is, up or down, um, then that device, so it's like if I'm holding your left hand and I ask you a question, you know that you're talking to me and I'm asking you the question, right? If I'm holding Matt's left hand,
You
and I'm
know that.
asking a
I know that,
question to the room
Max.
in general, Matt knows that I'm asking him the question and not you,
Right, right. That makes sense.
right? So that means you have to run another wire, which means you're using up pins.
Yeah. We already know we only have so many.
And we already know we only have so many. Um, and but it can be much faster.
Yeah.
Because you don't have to wait for people to shake the trees to see if anybody else is sitting on them. Um,
Yeah.
right? You just you go and you say, okay, I only have one person who's in control of this communication systems, and that is main. And main can pull the chip select lines. And if it wants to talk to everybody, it can pull all the chip select lines.
Right. It just needs more pins.
And if right, but let's say this, both you and Matt, right?
Hmm.
And if I want to ask you both simultaneously what you had for lunch, if I'm holding both your left hand and Matt's left hand, and I say, who had what for lunch? Okay. And then you can respond and say, sausage biscuits or whatever, right? Um,
Yeah.
and Matt can say his other thing.
Yeah.
But typically that's more like you would typically send a command to everybody like blink your eyes, right?
Oh, yeah, yeah, yeah.
So if I'm holding your left hand, I say to the room in general, blink your eyes. You know I'm the
Mhm.
one that you're the one that I'm talking to, right?
Yeah, yeah.
Um, but if I'm holding the hands of everybody in the room and I say blink your eyes,
Mhm.
and everybody's connected, they go, oh, okay. And we all blink our eyes. So
Mhm.
that's typically how that
So
works.
I don't know how to put it in like chip terms,
Hmm.
but for our example, would I know that like other people are giving signals too? Would that affect me at all, or is that just independent of it?
What happens is, so you have the bus wires coming to you, right?
Mhm.
It's S clock and no S clock. No, it's SCL. No, SCL is for I squared C, and SCK is for SPI. Um, and then there's another one for data, which I don't remember the name of right now. But it's SDA for, you have to just come up with an acronym so that you can communicate about it like person to
Yeah,
person. Um,
yeah.
so, but that's three wire communication, right?
Oh, okay.
You need to have one chip select line.
Mhm.
And you can hear what I'm saying to Matt,
Yeah,
right? But as long as I'm
yeah.
only holding his hand, you're
It
not going
doesn't,
to
yeah.
act on it.
But like I can receive like queries and whatever, but can I receive like responses? Like, do I know what Matt had for lunch? Or like would that affect me at all? Or am I even able to receive that information?
So everybody has the same two wires.
Oh, okay, okay.
And you'll see this. So they have the same two wires, but then they have an independent third wire. And
Oh,
you'll
okay, okay.
see this because there's a yellow wire that connects from the it's mostly MISO is what it is. So it's main out serial in.
Yeah. And then Mossy, right, is the other
Right.
one.
Yeah, so that's main out serial in and MISO is main in serial out. So in
Yeah,
fact, it's not a clock protocol. Um, it is an in out protocol,
sure.
right? So main only talks on the main out line, and serial only talks on the serial out line to main in.
Gotcha.
And so then you just assume that everybody's talking at about the same speed, and you have some tolerance for that. And then everybody on the bus can hear everything, but only the person
Gotcha.
with their chip select line pulled, well,
Can
person, but
respond.
only the device with their chip select line pulled will act on whatever it is.
Gotcha. Only one person can hold the talking piece. Well, no, no, no. You can only talk if you have the talking piece.
You can only talk if you have the talking piece, except
Yeah,
for main, which can talk to everybody over the main outline.
yeah, yeah.
She's the mediator.
Exactly.
No, she's actually in control. She's the empress of the
Yeah,
communications, right?
yeah.
So when she says anything on the main outline, everybody hears it.
Gotcha.
But
Yeah,
only the people she pulls on their particular wire, um, only those people will act on it. So again, typically it's, query, like give me the value for whatever. Um,
yeah,
like what did you have for lunch? Um,
yeah.
and if everybody could respond to that, they would all try to respond at the same time on the uh, main in serial outline. And so some
Mhm.
of them would be trying to pull the line up to 3 volts, and some of them would be trying to pull it down to 0 volts. And then the voltage level on that line is indeterminate and not in rhythm. Um,
Mm.
so that doesn't work.
So the logic analyzer?
It's the logic analyzer.
Oh, perfect.
So what the logic analyzer lets you do is it lets you snoop on those communication lines. Um, so you have to put some software on your computer, which is freely available,
Mm.
and then you plug that thing into your computer, and then you connect to either the two lines of the I squared C bus or the two lines of the SPI bus.
Mhm.
And then when a command
This.
comes across, it tells you what that command means.
Oh, cool. This will be neat.
Yeah. I can't quite see what you're doing, so I can't give you
Oh,
any
I was
guidance there.
explaining
Okay.
it.
Yeah, yeah.
Like reading all the things and looking at the
Yeah,
lines.
yeah.
Yeah.
So that little box connects to your computer, and then the wires on that little box connect to the other end of that little box. So it's like a voltmeter, and that all it's doing is it's looking for the voltage, whether it's high or low,
Mhm.
but it knows the rhythm patterns. Um,
Gotcha.
right? So it's listening to the drum beats and it goes, oh, okay, well, that means so and so. Yeah,
Yeah. Hmm. Very cool.
it's neat.
Yeah.
And it lets you do things in a much more compact way than you would otherwise do. Previously,
Yeah.
you would have to send a wire everywhere that you wanted something to do. Right? That's a lot of wires. Um,
Yeah.
and in fact, in automobiles nowadays, um, they use something called a CAN bus, which is a controller area network. So it used to be that you would send a wire to the left brake light
Hmm.
all the way from the switch at the brake pedal. And you would do that
Hmm.
for every device in your entire car,
Hmm.
right? Now you send power, ground, and signal and clock, I think it is,
Hmm.
for the CAN bus. So you just run four wires everywhere. And everybody is on the same signal and ground, or not signal and ground, signal and clock line. And then everybody has an address,
Yeah.
right?
Oh, that's
So
cool.
what you say is, hey, left brake light, turn on, right? So, hey, Bianca, make a sandwich. Um,
Wow.
yeah, I didn't say make me a sandwich.
Fair enough. Fair
Make
enough.
yourself a sandwich.
Fair enough.
And an appropriate response on that bus is no, right? So if
Yeah.
you, so let's say you have a brake light with a burned out lamp.
Mhm.
Okay, I'm fairly certain at this point that they're sophisticated enough to know this. Um, if the command comes to that brake light and says, "Hey, turn on," the brake light might say back, "Not able to,"
Mm-hmm.
right? Um, which for human beings, if I said, Bianca, make a sandwich, you could say, no, I don't want to.
Yeah.
Um, right? This communication is always in two directions.
Yeah. So then does that like is that what signals like the note on the dash like brake light out?
Oh,
Like
yeah.
when
So
it gets
there'll
the no,
there'll be a
it'll
bunch
signal.
of conditions that the car will look for, and
Oh,
it'll
okay,
turn on
gotcha.
the service light or something. Um,
Gotcha.
so yeah. And brake
Hmm.
lights are the simple one. Um,
Yeah.
like
Yeah,
controlling
I'm
the
sure they
fuel
get
injection is a whole lot more complicated. We have for the um, for the microcontroller that we're using in Stella 1.2, we have they call it a feather wing. It's a little extra board that can sit on top, that can talk to the CAN bus.
hmm.
So it's like that little box that you were just picked up, the little tiny box, the
Yeah.
logic analyzer. Um,
Mhm.
but so what that means is that we can then take a Stella. Oh, and remember that like those pins that are sticking up off the top of the processor on the board, right? And
Yeah.
how you have to keep them clean of solder because we might want to connect to them later.
Yeah. Oh, that's what we would
That's so we can
connect.
put a CAN bus wing on it. Or so
Oh,
we
very
can put
cool.
a radio wing on it so that we can communicate by long range, low power radio. Um,
Gotcha, gotcha.
so
That makes sense.
yeah. So you have to pull the cover off to do that because there's not enough room otherwise.
Yeah,
But and you need a bunch of pins, and so I was trying to keep two pins free for that system.
yeah. Very cool.
Okay, so we learned about USB, we learned
Hmm.
about I squared C, we learned about
Hmm.
SPI, and we learned about CAN, right? That's a whole lot of
Yeah,
communications.
yeah.
And
We're
then just,
communicating about communications.
right, communicating about communications. So all we're doing is literally banging rocks together to tell stories. Um,
Exactly.
right? You turn on a transistor, it's a way of banging rocks together. The rocks are electrons and the transistor is made out of silicon, but whatever. Um,
Yeah,
yeah,
it still rocks.
it still rocks.
Still rocks.
And if you think about how many of those are happening in order for us to have this conversation over this link, um, yeah.
Yeah, yeah.
Oh, and then there's one other that you should know about. Um, so there's Bluetooth, which I haven't researched. I don't know how it works. But I think it's a variant of the same thing. So Wi-Fi, right?
Hmm.
I'm using Wi-Fi.
Hmm.
Um, and how that works. So how can you have a whole bunch of devices on the same radio network that aren't stepping on each other? Right? We have all of these like cell phones all over the place, right? You can't have one frequency for everybody's cell phone,
Yeah.
right? Because there's just not enough frequencies to do that. Um, so how does that
Oh,
work?
I think we talked about this. This was Hedy Lamar's thing, right?
Yes, Hedy
Where it would
Lamarr,
just search
you
for,
got it.
yeah, yeah. It
Excellent.
would search for an open channel, so that way it like switches every time,
It's not
and
even
it's
that
harder
it's
to
searching
track.
for an open channel, it's that the pattern. So, like, let's say you have, six different frequency channels, right? It's the pattern of going from one channel to another channel that
Yeah,
makes the information.
yeah,
She called it frequency hopping.
yes.
And I think nowadays we call it spread spectrum.